So my talk will be based around these new types of architectures of AI models and basically architectures of neural networks for combining physics with machine learning and deep learning. So that's why this is the whole presentation is called PhysicsML or SciML. That means scientific machine learning. And I will be talking about how we can harness this new power of AI for technology development. I will be talking about technology development, product development, but also other things, how we can use AI in the healthcare industry, and then extrapolate to how to pick the right technology for using that technology in the healthcare. So first of all, just some information about me. My name is Michal Takáč, and I'm a co-founder and CEO of DimensionLab. We are a company here in Košice, based in Košice. We develop a software platform that uses that basically provides an interface for creating, using, training, and deploying AI-based simulators. So leveraging this technology that I will be speaking about on this presentation. So first of all, we need to think about the world around us. It's not static. It's not something that doesn't move, and it's not something that we can model or reduce the complexity of it in such that it's static. We still need to kind of get to a level that we rely on dynamic system, or think about in terms of dynamic systems. So I like this this comment from Niels Ture. It's a guy who developed a new data-driven numerical methods, like data-driven AI methods for simulating Navier-Stokes equations and etc. And he says that we really need to kind of focus on understanding the environment around us, and that's the key challenge to understanding the environment and know how it evolves. Then we can design or use this knowledge to design new algorithms and rethink how these algorithms are used for learning more about the environment around us. So stuff around us, everything that is happening around us can be somehow described by mathematically, and usually how you do it with with partial differential equation. So a lot of systems, a lot of processes in nature around us you can describe in this way, and we did that for the past hundreds of years. And the mathematical toolbox evolved with us, and we now have a large knowledge and large history of doing that, which is great. But since world is evolving, everything is evolving, and also a problem at hand the problems at hand are also evolving in a way that they are more and more complex. So it's much harder for us humans to actually design new types of algorithms, design new types of mathematical formulations to understand the world around us, basically. So we now can leverage these new types of AI architectures to help us with that. And this is coming up from a new ways of how you can combine a data-driven scientific machine learning models that, I know a lot of you maybe take it as a black boxes, and you are pretty much hesitant when you think about this, like how can something that we don't understand be used to help us to understand nature if it's a black box. But I will get to it in a few minutes. And I think it's a problem around just it's too early for us. We still need to do more work in terms of trying to kind of learn more about these types of architectures, these types of models, come up with new ones, and study how the training processes can be kind of like analyzed. So going down deep into understanding and trying to create new explainable AI models. So the problem with black boxes and kind of these data-driven models are slowly mitigated with these new types of AI models called physics or the AI methods that are called physics-driven machine learning, or PhysicsML, or scientific machine learning. This is encompassing the same thing basically. And with this way, you are able to incorporate the information or the knowledge of some mathematical formulation into the neural network itself, which is a huge thing actually. And you will see in a few minutes why. And the last thing, which is also a great thing for me personally, and I guess for all of us who want to kind of find a way how to run the simulations, the numerical simulations faster, is that these types of models, after they are trained, can be used for simulations with extreme speedups, up to hundreds of thousands times faster than the traditional simulation software, which is actually crazy. When we, from DimensionLab, if we went to some clients and said this to them, they were like, no, that's not possible. No, so we needed to educate. So coming back to the notion of black box, we all kind of are not trusting that much if it's something that we don't understand because it's a black box. But since scientific machine learning is still very, very new, we just have to take more time and study it more to come up with better ways to actually work with these types of methodologies and create new ones that are much better to be explained or something. So, but if we kind of go back to history, how numerical methods came by, they were also plagued by problems with numerical instability. We took large efforts to actually work this out. So it took tens of years and decades to actually work around this. And I put a sorry, there's not a laser. I put a kind of quote here that some people were saying that these instabilities were considered actually at the time to be the constant source of anxiety in the future. So we will never figure it out. We figured it out. It just took some time. So I think that will be the same case with these black boxes of data-driven methods. On the other hand, we don't have to rely only on data-driven methods if we have the history of developing these awesome numerical algorithms that kind of, we have this history of developing a large number of discretization schemes and solvers with this, or incorporating physical models into them and making them better and better over time. So why not to remove this information or just not use it if it's there, if we know about it? Why not include it in the neural network itself? And so that's what started happening from, I think, year 2017 with the introduction of physics-informed neural networks, where there was shown that you are able to kind of create a loss function from the physics itself, from the mathematical equation, from the parts of mathematical equations. So very interesting thing. We will be talking much more about this again in few minutes. So yeah, the scientific machine learning is also the subcategory of artificial intelligence, and machine learning is subcategory of artificial intelligence. That's the same thing with deep learning, and SciML or scientific machine learning is the subcategory of deep learning. So it's a method that combines machine learning, deep learning, and physics-based modeling together. And what we are trying to do in this area is to kind of optimize the techniques that we develop in this area to get to better prediction performance on these models, but also to improve the efficiency of sampling some sample data. So we don't want to work with large numbers of data, because usually or I would say usually you are not, they are not provided for you. So if you have some sensors in some processes in manufacturing, you are able to extract data from it and get large amounts of data, and you can create your data sets, but mostly not. So you rely only on the physical model, you rely only on some older simulations. So what we want to do is to remove the need on having large amounts of data. And of course, another very important step or a very important objective here is to improve the interpretability or understanding of the whole architecture and the training process and what happens when the model is trained, what is inside that model. So remove the notion of black box. And it's not easy thing. So as Fuzia said, and I thank you for the introduction into this topic, because I don't have to tell you that much about it from now on, and I can spend some time on more interesting things. But as we were mentioning before, that there's a different approaches to working with machine learning methods, or like how to leverage machine learning methods. One is using data-driven approaches, so supervised approach. And in scientific machine learning context, that means that we can extract some simulation outputs or have multiple iterations from simulations and use that to train it's called surrogate models, or something that you can remove the older model and have this only AI-based model, but it's trained on the data from older simulations. But if you can imagine, that means that you would need to create large amounts of data through simulation software, which will take you weeks, maybe months, maybe years. So it's extremely hard to do this. But sometimes there are institutions that store their simulation outputs, and they can just leverage the data that sits on their servers, and that's great, but that's, again, not usually the case. And another thing is to do it with the unsupervised approach. Here in scientific machine learning area, that means using physics models or mathematical equations to extract the loss function from it, or to use kind of like physics understanding and bake it into the model. And you can use PDEs for that, but also boundary conditions can be used to create this kind of a loss function for your model. But the main point for the future reference is that we should be able to combine these two approaches together, because then you would be able to make the models much, much more accurate, having a data that is trained on, but also baking in the physics understanding, if that's possible. So I want to show you some key components of this revolution that is currently ongoing. And as I've said, the first kind of step in this direction was introduction of physics-informed neural networks. These were developed in 2017, and it's sparked a revolution, or like this very interesting research that started from then and still ongoing, and it's a very hot area of research. So the families of these types of architectures, just taking Fourier neural operators, there are now tens of different types of architectures that I even don't know which one exists, because there's a Cambrian explosion of specifically neural network models for scientific machine learning. So as I've said, things are basically ways to incorporate your physics laws into the neural network. Fourier neural operators is something like having a way to transform your inputs into these neural networks are functions. So some variable how vibration changes across time, something like water flowing into the river and changes across time. So you have variable inputs in continuous equations, and you can use Fourier neural operators to kind of do the convolutions throughout the training process. and it helps in some cases where pins are not sufficient enough. Let's say you have a problem where there's a geometry of something that is very sharp edges, and you cannot model it because it's super hard to do. You can constantly zoom in into that corner, and you will never get the right physics there. But for Fourier neural operators, it just converts it into a kind of like how to say it, signal space or something like that, and then it uses Fourier operations on that signal, so it doesn't get into problems where you can get stuck with pins in the local minima when you're training it. There are another additions. I mentioned basically the adaptive Fourier neural operator because I will show you in a few slides. It was used for a very interesting modeling of weather predictions. Then there's like combinations of using physics-informed learning with neural operators, so you can combine those. And very, very interesting architecture is deep operator networks, and that basically combines two types of networks that do something different with inputs and something different with outputs, and you kind of create this connection between the inputs and outputs, input functions and output functions. And using these types of network, you can train the network to be very well generalized, meaning that if you train it and you put some input variable that it didn't see, it can predict the right value out of it. So since we are basically, I was spending a lot of time researching what are the frameworks, what are the tools right now available for working with these types of neural networks. I stumbled upon a very interesting framework called NVIDIA Modulus. So also this presentation will showcase some code, some use cases that uses Modulus for these things, for some practical things. And also I added here a QR code for great course from ETH Zurich, and it's about deep learning and scientific computing. And I encourage you to look into it and see for yourself. There are multiple kind of lectures, very good. So, yeah. So, looking into some practical things right now. As I mentioned, NVIDIA Modulus. Here is an example how you can leverage AI-based modeling for creating a kind of like simulation model or simulator model that can have multiple things inside it that can be used for one, optimizing the design itself, but then doing analysis on the geometry itself, and doing it in a parameterized way. Now let's go through each of those things that I mentioned, so you understand what I'm meaning by that. So here is an example how you can define different geometry, different geometries in a parameterized way, meaning you have some variations of these fins. You have some thickness, you have some ranges between them, you have some lengths, some width, etc. And what you can do, you can actually take all of these variables and make those a symbolic variable. So then if you have a symbolic variable of that, you can put a range to that symbolic variable. So when you provide this information to the model in a modulus symbolic or modulus sim, when you train the model, it will be trained for all of the ranges of the inputs. So after it gets trained, this is the great thing. Once it's trained, you can just do the inferences, and these inferences are extremely fast. So doing analysis and changing the parameters and then resimulating the output would take you 2 seconds. So instead of waiting 1 week or a few hours to do a very complex simulation, you can do it literally in seconds. And if you pre-train it correctly in a right parameterized way, you can have a large model that that inherits all the information with parameterized variables that you can then change the input resimulate it again, have the output, and you can do the analysis literally in minutes. So what you can parameterize in modular symbolic, it's not just geometry. You can parameterize also equation variables or equation itself. You can parameterize also the constraints or boundary and initial conditions. So you can put the same ranges on something like velocity, the inlet velocity, and train it from, let's say, some flow. There's some input flow, and it should be trained from these flows from 1 meter per second to 10 meter per second. So you then, after it trains, you only do the inferences. So you should be able to train it once. Again, I also included some QR code for you to check the code for this, so you can play with it yourself. And now just extrapolating to real-world experience, it's the same code, nearly the same code. The geometry is different, but this was used by NVIDIA to optimize their heatsink. And they used to do these types of simulations for months. It took them literally hundreds and even thousands of hours of simulations in commercial software. And what they did is that instead of kind of manually going to different variations of the shape of the heatsink, they parameterized the geometry and trained it once with all of the information put into it. So all of the equations were parameterized, all of the constraints were parameterized, and you basically then could do something like change the shape of the geometry itself in different ways, and you can run the simulation interactively. Or what you could do actually is, once it's trained, once you have the model, you can write a script that you are then asking that model to generate optimal solution for you instead of you doing that manually. So you don't have to change the input parameters. You can write a script, find it for me. And yeah, this simulation is run 75,000 times faster than the traditional one from commercial software. Now we get to, this was a glimpse into, like the previous slide was maybe some glimpse into where we are going, and that's kind of this notion of combining these new types of AI-driven simulation models with digital twins, and also this notion of creating multiple digital twins with multiple AI, multi-physics models, and connecting them together to create this sort of like industrial metaverse. And this is a kind of buzzword that is thrown around very much lately. So we came from normal metaverse, now we are in industrial metaverse, and we will see what that will look like. But basically the notion or the goal of people who were developing these digital twins was to get to a way, get to a point where you would be able to leverage digital twins in real time. So you can do the experimentations very fast, or see all of the real processes that are happening in the factory or somewhere else in the digital twin. And you can do some predictions and see what will happen if something happens. So now with these new types of AI models and AI architectures, now it's possible to combine those and to create such digital twins. So this is some example of digital twin created in NVIDIA Omniverse combined with NVIDIA Modulus framework to pre-train the model for a heat dissipation and heat transfer throughout the data center. So what they did previously was that they did multiple simulations for different slices across the data center. So they need to run the simulation for, I don't know, meter above the ground, another simulation for 10 meters above the ground, and so forth. And it took them large amounts of hours on supercomputers. So it cost them a lot of money. And with inclusion of pre-trained model and parameterized pre-trained model into the digital twin, they were able to not just see the real-time kind of data coming into it, but do the predictions again in near real time to see how something would change if there was a sudden heat rays or something, or if they needed to change some components, or if they add I don't know, if they add more components to the data center, and what will happen, and see the 3D output of the simulation and change the slices slices interactively instead of rerunning the simulation again and again. So this is how the Omniverse looks like, and I wanted to show you the interface. If you wanted to use it and explore it, you would first have to download the NVIDIA Modulus toolkit or something like that into the Omniverse itself. And then they provide in the documentation the snippets of the code, how you can prepare your simulator to be included in the Omniverse. And once you do it, there are actually some examples that you can run, and they are already pre-trained for you, so you can play with them. This is actually the same thing that I showed you previously. It's a flow through the heatsink, or the three-fin thing. Yeah, there's actually a heatsink because it has more slices. Sorry. So you can prepare your NVIDIA Modulus simulator in a way that if you load it in the Omniverse, we'll get this nice UI inside it, so you can change the parameter, run the simulation again, and change it again, run the simulation again, and you can see everything here in the Omniverse. But once you are in the Omniverse, you can create high fidelity simulations and animations there. So this is static, but if I had a video from this is actually very nice when you put the visual of how the heat is flowing through this, and you can change the slices, and you can see everything recomputed in near real time. So it's happening in front of you, and really like interactively. And that's really awesome that you can run pretty complex simulation in a few seconds. And again, to go from a very simple example to something extremely complex, but again created in Omniverse. This is a digital twin created by Siemens Energy, and this is a digital twin that combine pre-trained AI-driven simulations with Modulus of water flow through the pipes of some factory, and they are trying to kind of see how the corrosion will kind of be created or something, and they want to prevent that. So this is kind of like predictive maintenance of the pipes to prevent the corrosion. And they have multiple models created for it and deployed in that digital twin running at the same time. So you can create these types of animations pretty easily there. So now I'm jumping into different industry, but stay with me, please, because I want to showcase a pretty interesting use case from healthcare industry. So previously you would maybe you get used to seeing these new types of models, or not models, but if you want to leverage new types of AI models, they're usually in a healthcare industry used in a way like you have a 2D image and you are trying to see some anomalies in that. And they are usually using convolutional neural networks and different types of other networks, but you would nearly never see some simulations or predictions. I'm not saying about some hardware that is already it has something like simulations of flows through some parts in the body, but this is I'm more saying about a software for doing the predictions, doing the simulations. So here in this case, if we are trying to prepare a diagnosis or create a better diagnosis for a patient with aneurysm in their brain, it's super hard to do that for different patients with different geometry of their arteries, of their basically blood vessels and everything. And what you can do is to go through an MRI scan or a CT scan and get the geometries out, but you have just the geometries. Now you need to create a CFD simulation of the blood flow in your brain, basically, and that's super complex. because again, you would need to run the simulation for every patient, not once train it and then use for all of the patients. But leveraging AI-driven modeling, it's possible because now you can pre-train the model on, first train it on one complex geometry, and then when another patient comes, you can do the transfer learning, which is much shorter than the previous training, and kind of pre-train the model for these different physics phenomena inside that blood vessels. So we can then analyze how the blood is flowing through the blood vessels, what to do with that. As you can see it in real time, you can act in minutes instead of waiting like a week for the simulation to finish. And this can possibly bring a new types of diagnosis tools on the table. So maybe you can do a prediction how the patient's state will evolve for the next few days, weeks, months, whatever. Or then which type of technology should be used to kind of fix his state. So I'm not really understand. I don't understand that much the ins and outs of these types of problems. But if we can get to a diagnosis much faster and get a prediction, I think that the doctors and all of the stuff around that will get a new thing that they can leverage and kind of move forward much faster, so more people can be saved in time. And yeah, for this specific problem, again, physics-informed neural networks were used. We also have in our company pre-trained few of these types of models and seen this ourselves, that you can generate this flow of blood through the aneurysm and see the pressures and everything literally in 3 seconds. That it's crazy. Now jumping into other industry, what you can do with these types of AI-driven simulations is to optimize wind farms, but in different way than it was done previously. Previously, you had to you had to reduce your modeling into very simple models because you cannot do high fidelity simulation for wind turbine. It will take you 30 days to actually simulate it. So why you would do it? You want to create a kind of analysis where to put the whole farm, what is the relief of the country, or what are the kind of like weather states, or how the weather is in that area. And based on that, you are doing this manual kind of like design and analysis of what might be the optimal solution of that farm at that place. But here, you don't have to rely that much on your manual or like human intuition. You can just ask your model to create a optimal solution for you. So now we are able to pre-train the simulation through of the wind flowing through the whole wind farm instead of just one wind turbine, and also check some turbulences, check how one turbine affects another one's, check how different weather prediction will change the energy generation. And then once the model is created, we can combine the weather outputs with the model and generate the optimal solution for me for this country part where we want to put it. And this specific optimization took Siemens Gamesa, this is the company which developed that, 7 minutes. So this takes 7 minutes to do. Sorry? It took them a few months, and once they trained it, they can use one model that they trained for different places, and it's once trained, of course, that might be new data coming in from the weather predictions, so they can just learn the model and just add new data to it. It's pretty simple to do that. Then run again the simulation. But yeah, we talked with Brandon, actually, our colleague, that we were talking with people who built wind farms, and it's not that easy to convince them, like, from now on we will be all using AI types of models. No, everybody is using WindPro software, so it's still a large part, or like a long journey to get to a point where we can kind of take over WinPro software, and guys from different banks can then give money to people who build the farms, because it's not that easy to get kind of like validations and all of the stuff around that. The weather prediction modeling. This is a very interesting case because like the weather modeling is a super complex problem. We spent tens of years on this modeling problem, and there were a large amount of people working on that. We have a lot of experts in this area, and that then a lot of mathematical models were prepared. And right now we are relying on a ECMVF model for the forecasting system, which is the state-of-the-art weather prediction model that generates the weather prediction for 1 week forward. And they spent 3 hours on supercomputer to generate that prediction. Now, imagine if you can train the model on the historical data and get the same accuracy for generating the week-long weather prediction in 13 seconds. It's possible, and on your laptop. So you can get not just down on the computational speed, but also on the energy usage of doing that simulation. So at first, we actually tried this in our company. We wanted to see how, if that's even possible, if it's not something like just some buzzing around from NVIDIA, and we ran actually the digital twin of, we actually run the forecast net ourselves, and inside the digital twin in Omniverse, and it on my laptop with some GPU for gaming, it took literally 13 seconds to generate the output for 1 week. And yeah, of course, the accuracy is a bit less. The resolution is also a bit less than the state-of-the-art model. But this was developed 1 year ago. 6 months ago, they have new model, which now has 8 kilometer resolution per pixel. And it can generate a weather prediction for 6 months pretty accurately. So I imagine what will be next. 1 year, 2 years, 10 years, I don't know. But like everybody dismisses this because there were never correct prediction from weather prediction model for more than a week. And usually it breaks down after 3 days anyway. So we'll see how this will go. But anyway, if we are now able to run the weather prediction on our laptops or maybe a bit beefier servers, we can then connect these into our services or some other services that we develop. Something like we can predict what will happen if there will be a cyclone coming, or if there will be a change in some wind direction, change in precipitation. So we can use these predictions for other applications, for agriculture, for I don't know which industries, but there are many different. There are definitely much more that can be used or can be connected. Yeah, I also added some visualization of how you can try putting your house near some nuclear power plant and see how it will change if the weather changes. So it's not the best position. And with these types of models, you can do this interactively, so you don't have to rely on supercomputers to do such simulations. And I wanted to showcase also something from us, from DimensionLab. And we were approached by a company which developed a model for river flowing into a small hydro plant. And now the problem was that they spent large amounts of time on the extremely complex problem. They didn't have that much money, much resources, too much people for such hard problem to solve. So they spent a large amount of time on that. And we thought like, okay, maybe this is pretty interesting opportunity for a smaller company to leverage this new these new types of AI modeling, can we get to accuracy of commercial solvers for these types of problems? And it turns out that we can get pretty close. And what we did was that we created few of these AI models. First, it was some custom coding, but then we started implementing some features, some kind of like information about what we learned from creating such model into the product that we develop. And here you can see actually an output from the simulation that is nearly as accurate as the one from commercial software, but we actually created 6 types of these simulations or simulator. We created 6 simulators with different architectures in 3 weeks instead of spending 4 years on these problems. So now it shows extreme reduction in time that you want to spend on modeling something like that. And we thought a lot about how to create a great user experience and simplify the modeling part. So we came up with this visual editor that you can now use in Siml.ai, our software that we developed for these types of AI models. So here you only focus on the physics at hand, on the problem at hand. So you have some geometries, obviously you have some equations that go inside it, like Navier-Stokes. Then you have some constraints, so initial conditions, boundary conditions, and you just combine those together in the visual editor. You set settings on all of the constraints. You prepare the parameterization of that simulator in that visual editor. And then with one click, you deploy it into training on our infrastructure, and you just check how the model converges. And that's it. So instead of reading documentation and learning about all of these new paradigm with AI-driven modeling and getting into knowing how to manage cloud infrastructure, which is pretty complex if you want to leverage GPUs for training your AI models. We found a business model that is pretty interesting to kind of like simplify all of this and merge it into one cohesive platform. So this is a segue to what we provide actually. And you can also see here, this is one server that was running on a A6000 GPU, and and it took 17 hours for one simulator model to be trained, but this one is parameterized, so it already knows, or like it already has the knowledge about different inflows of the water in different inlet velocities. So we can change a velocity to 0.5 meters per second, change the velocity to 10 meters per second and see what will happen. And we can see very nicely how this part is not designed properly. So then the analysis is much faster, so we can see where's the culprit, which part is wrongly designed and should be redesigned. And obviously the next step would be to use a kind of parameterized geometry, so we can create a model that creates the optimal solution for the company instead of doing this manually. So Siml.ai itself is split into 2 parts. The first part that you also seen before in the previous slide, this is mainly about the visual editor. So we provide a building blocks for you to very simply create these types of AI models or AI simulators without coding. So it's a no-code tool basically. You only think about the problem at hand, the physical constraints, the physics model that you want to use, what equation you want to use, and etc. And then another part is a simulation studio. So we thought about like why to kind of let people to install different types of software, which is really hard to do. Actually, when going back to Omniverse, it's nice interface, but getting it to run on your computer, try it. It's super hard. You need to have Linux machine on NVIDIA GPU. You need to set up everything correctly, and it usually crashes. But after a while, if you have beefy software and you have all of the VNC set up in the right way, it will work. But why not to simplify also this part, creation of the digital twins for you? Once you have the AI model trained, you want to use it, not just download it and you go to another software. So we created a simulation studio which does exactly that. So once you train the simulator, you can preload it and use all of the features that is inside that. So if it's parameterized, it will showcase a UI already for you, which you can just change the input parameters that you provided and click the simulate and you get the output. Of course, we are only in beta, so far we only have the static simulation. But in the next 2 months, we will be releasing in transient simulation support. So you will get an option to see the animations, how the flow actually goes through it. No, you don't have to rely on changing only the input and seeing the static output. And of course, we want to be modern and try to explore new things. And since I was inspired also by some talks by Timmy Girau just recently, he was talking about world building and virtual reality and stuff like that. And the great thing about the underlying infrastructure that we have is that we can very easily connect that to virtual reality. So in near future, you will be able to use Simulation Studio inside your headset and basically do the simulation interactively in the VR. So the ending thoughts, this technology is still just scratching the surface, but I think it has a great potential, as you could see, hopefully, from the presentation. And not many people know about these types of architectures that I was speaking about. So I want to put this forward, and also it's great that you heard about that, and I hope that you will share that with your colleagues and maybe spread the word. So yeah, thank you very much.